Okay, the third lesson in energy resource and energy transfer is on work and power. Now this involves 4 equations. This is a very mathematical topic. As long as you know these 4 equations, then it's fine. We're looking at energy, but we're looking at this in a mathematical way now. So we're looking at work done, or energy, as force times distance. We're going to look at gravitational potential energy, kinetic energy, and power, the rate of energy transfer. Alright? So the first one then, the work done on an object equals the force times the distance that you apply the force for. Now work done is exactly the same as energy, so it's measured in joules, force is measured in newtons, and distance is measured in meters. So our first equation for energy, work done, is force times distance. So if you were to push, if you pushed a suitcase, for example, and you pushed it with a force of say 100 newtons, and you did this for say 6 meters, then the work that you have done on the suitcase would be 100 times 6, which would be 600 joules of energy. That's how much work you would have done on the suitcase in pushing it with 100 newtons for 6 meters. Now, the next equation is kinetic energy. Now, kinetic energy, or movement energy, equals 1/2 times mass times v squared, or mv squared divided by 2. There's another way of writing it. Now, this is the other way you write it is mv squared divided by 2. Now, this energy is anything which is moving has kinetic energy. So, for example, if we think about a 6 kilogram ball, and if a 6 kilogram ball is moving at say 5 meters per second, then it has kinetic energy. So we would say its kinetic energy equals 1/2 mv squared, which is 1/2 times 6 times 5 squared, which is 1/2 of 6 is 3, 5 squared is 25, is 75 joules. So the kinetic energy of an object is mv squared divided by 2. 1/2 of its mass times by its speed squared. Now, the other one is gravitational potential energy, and that equals mgh, where of course remember m stands for mass, g is the acceleration due to gravity, or the force acting on each kilogram, which we know is 10, and h stands for height, and of course height is measured in meters. So for example, if we have a 4 kilogram ball which is say 5 meters above the ground, then it has the potential to fall. It has gravitational potential energy, which we would say is mgh, which means it's got 4 times 10 times 5, which is 200 joules of energy. Gravitational potential energy. Okay? Now, before I go on to look at power, I just want to look at these equations in a bit more detail and start to put them together slightly. So, gravitational potential energy, which is mgh. So we know gravitational potential energy is mgh. We know work done is force times distance, and kinetic energy is 1/2 mv squared, or mv squared over 2. So let's think about this. If we take a 4 kilogram ball, and I want to lift this 4 kilogram ball up to a height which is 3 meters above the ground. In order to do that, I need to apply force, but we remember from our forces topic that the weight of this is mg, which is 4 times 10, which is 40 newtons. So in order to lift it, I need to apply a force upwards of 40 newtons, or 40.001 newtons. Now, as I want to lift it 3 meters, I need to apply a force of 40 newtons for 3 meters. So the work I would do on this ball equals force times distance, which equals 40 times 3, which is 120 joules. That would be the energy required, or the work that I would need to do in order to lift a 4 kilogram ball through a height of 3 meters. Now, because of the principle of conservation of energy, that must be exactly the same as the gravitational potential energy it will have when it gets there. So just to check that, the gravitational potential energy is mgh, which is 4 times 10 times 3, which equals 120 joules. So the equations are related. They come from the same place. Now, a more complex question on this would involve maybe gravitational potential energy and kinetic. So let's think about this example. If we take a 2 kilogram ball and it is a height of, say, 10 meters above the ground, and we could say, if this ball was to fall, what would be its velocity the instant it hit the ground? So you would say its gravitational potential energy at the beginning is mgh, which is 2 times 10 times 10, which is 200 joules. So this ball has 200 joules of gravitational potential energy. When it falls, as it falls, because energy is conserved, when it's halfway down, it's lost half of its gravitational potential energy. It's lost 100 joules, but those 100 joules are now kinetic energy. And as it falls further down, it gets faster because the gravitational potential energy is changing into kinetic energy. Now, the instant it hits the ground, its height is 0, so it has no gravitational potential energy. All of that 200 joules are now kinetic energy. So if we wanted to know how fast it would hit the ground, we could say we know that 200 joules, which is what it's got, what it started with, equals a half times mass times v squared. So we know then that in order to calculate velocity, we know it started with 200 joules, and that now equals, all of it is now kinetic, which is a half mv squared. So 200, a half of 2 is 1, so it's 200 equals 1 v squared. So v equals the square root of 200, which I think is 14.1 approximately meters per second. Let's check. I'll do it this way instead. Yes. 14.1 meters per second. So that's how fast this thing would hit the ground. Now, the last question would be relating to power. So, for example, the power of an object, the power of a machine, sorry, is the energy that it can transfer in a given amount of time. And power is measured in watts. And 1 watt is 1 joule per second. So if we think about, let's try and think about a more complex example. So if we think about somebody stretching a spring and they're pulling a spring. Now somebody, some muscle man, is pulling a spring. Now when they pull it with a force, and the force they pull it with, the average force, we could say is maybe 200 newtons. And when they pull it 50 centimeters. but they're really, really fast, and they're able to do this. We could say they do this 120 times per minute. We might be asked to calculate what is the power of this person's arm if they can pull a spring with an average force of 200 newtons, a distance of 50 centimetres, 120 times per minute. So firstly we'd say, well, because power is energy divided by time, what is the energy required to pull this? Now we know it's force times distance, which would be 200 times 0.5, because it's in centimetres, times, because he's doing it or she's doing it 120 times, we would times that by 120. Now notice, you pull the spring because you're doing work against the spring. You don't count going back again because the spring does that for you. You're not doing any work. The spring returns to its original length on its own. You only do that force outwards. So that would be the energy required in order to pull this with this force, this distance, that many times. Now the time was per minute. So rather than dividing it by 1, I have to divide it by 60. So we have 200 times 0.5 times 120 divided by 60 equals 200 watts. So in order to pull this spring with a force of 200 newtons by 50 centimetres, 120 times per minute, would require a power of 200 watts. The total energy transferred in the total time it took. It's important you can relate the three energy equations: work done, force times distance, gravitational potential energy mgh, kinetic energy being a half mv squared, and then once you've been able to relate all of those, you then need to be able to think about power in terms of the energy transferred per unit time. And that is an example of something you might be asked to do.